Hi Rob, thanks again for asking me to do an audio abstract on our latest paper, Mechanical Determinants of Faster Change of Direction Speed Performance in Male Athletes, which was recently published in JSCR. So if I take you through to the methods, what we investigated was a modified 505, where we inspected the ground reaction force of the kinetics during the penultimate foot contact and the final foot contact. The task consisted of a 5 meter entry, 180-degree turn, and 5 meter return as fast as possible. Each subject performed 3 trials each side. To take through to the results, performing Pearson's correlations. Faster performance was associated with greater magnitudes of horizontal propulsive forces in shorter ground contact times, with these being large and very large respectively. Interestingly, there was no significant relationships between vertical propulsive force and completion time, so this illustrates the importance of a more horizontally directed force vector in short ground contact times. Also, slower performance was associated with greater vertical impact forces in the final foot contact, showing a bit of a misdirection in braking force application by some of the slower athletes. And what we also found for modified 505 left only is that greater horizontal braking forces in the penultimate foot contact were associated with faster performance, and a greater amount of braking forces in the penultimate foot contact relative to the final were again associated with faster performance. I'll take you through to the fast v slow comparisons. So for the left side, faster athletes again produced significantly greater horizontal propulsive forces in shorter ground contact times compared to slower athletes, with these being very large and large. Again, they also produced lower vertical impact forces in the final foot contact, and also interesting, which shows some promising results about the penultimate foot contact. They also demonstrated significantly greater horizontal braking force in the penultimate foot contact and a better ratio, so a greater proportion of braking in the penultimate relative to the final. Again, quite similar for the right side. Faster athletes again demonstrate smaller ground contact times, greater magnitudes of horizontal propulsive forces, and lower vertical impact forces. An interesting thing was, irrespective of direction, faster athletes, there was no significant difference between faster and slow athletes in vertical propulsive forces, highlighting the ability to produce horizontally directed force as key for faster change direction speed performance. So again, the technical application of force could be a distinguishing factor. If we take through to the practical applications, so based on results highlighting the importance of rapidly producing propulsive and braking forces in short ground contact times, and with the previous literature indicating that strength is a pivotal component of change direction speed, we encourage practitioners and SSC coaches to develop their athletes' bilateral and unilateral strength and rate of force development qualities. These include eccentric, isometric, and concentric strength. Plyometrics should also be considered due to the similarity of the ground contact times and the similarities in the push-off action to change of direction. We recommend a turning technique with greater horizontally directed propulsive forces in shorter ground contact times for faster performance. And we also recommend that practitioners coach athletes a braking strategy which consists of high levels of horizontal braking forces in the penultimate foot contact and a high proportion of horizontal braking forces relative to the final foot contact for faster 180-degree performance. As with any study, there are a few limitations. We only examined the peak brake and peak propulsive forces, which is only representative of one data point. Further inspection of impulse and average force would have been a greater insight into the brake and re-acceleration strategies. In hindsight, we should have calculated resultant force through Pythagoras theorem, and we should have also calculated the angle of the force and the orientation of the force through some trigonometry. These are things that we're looking to do in our future studies. We only examined the ground reaction forces, but further insight conducting 3D motion analysis so we could get some whole body kinetic and kinematic data would also provide a greater understanding into optimal change of direction strategies. And we didn't standardize footwear, so the study didn't control for the effects of shoe surface friction. And more of note of caution than limitation, biomechanical demands of change directions are influenced by the angle of the change direction, but also the entry velocity. Therefore, our findings are only applicable to pre-planned low approach velocity 180-degree turns. Further research is required investigating the mechanical determinants of the traditional 505, where you would expect a higher approach velocity, and also change direction tasks of different angles such as cuts, and also unanticipated tasks. I'd just like to thank the co-authors for their help and input into the study. I'd also like to thank Phil Graham-Smith for the permission and use of his customized analysis spreadsheet,